This is the numerics part of the dynamical system tutorial. Very trivial and very simple, but I wanted to show that it's more to demystify, to show you nothing special happens as we do the numerical solution. So I introduced last week this notion of a dynamical system. So for a single variable x, the rate of change x dot, which we sometimes also denote by dx by dt, so different mathematical notation for the same thing. The rate of change is some function of x. So here this red function is some nonlinear dynamical system. And I emphasize that the core of that idea is that the present determines the future. That is, the variable, which can be vector valued, is such that if you just know the initial value of that variable or that set of variables, then the future is uniquely determined by the dynamical system. And we kind of intuitively argued by that by mental simulation that if you know the initial state, you can look up in this function the rate of change, and the rate of change will tell you the immediate future in some kind of mental iteration where you would then evolve the solution like that in time. And today I actually want to make that concrete. First, I'll review these concepts. I'll show you through numerical procedure how that's concretely done on a computer. Again, just to fix the jargon, this x we call state space, can be vector valued, and later it will be function valued. It will be whole fields that are characterizing the state. We call f of x the dynamics, or also the vector field. And a solution is a function of time in terms of these variables, x connected to an initial condition. And that means exactly that the rate of change of that time function obeys the equation and has as its initial state at t equals 0 or t equals some other initial time, has that initial condition as its solution. So I'll show you now how to approximate such things on the computer digitally. And on the computer, of course, you don't have continuous time. The digital computer is based on a clock that has some kind of cycle, discrete operational cycles, and therefore everything that you represent on the computer comes in discrete steps. So the aspect I'm talking about is really how to make time discrete. You may know that on the computer, any real number is also represented by a finite representation, so a limited number of digits that has to do with floating point versus integer issues. That's also a subtle issue, but I'll not talk about that. That's sort of in all programming languages that is delivered to you. Famously, the C programming language was really terrible on that count, but modern languages provide you with ample concepts for that. Those who know the sort of stuff might remember that it was a question of double precision in the past versus simpler representations. So we take that for granted, that we can represent real numbers approximately by what ultimately end up being finite numbers. Representations as rational numbers. So it's about the time being discrete that we worry. So any continuous time function will be represented by discrete samples. Samples will be integers, up to some, can be numbered. And so the index is an integer up to some number. And the example I will be talking about is the simplest one, where it's equidistant, which is not the state of the art. Modern simulators use variable step size depending on how articulate the dynamics is, how much change there is. But we'll just look at the simplest case. So simplest case is you have a constant time step delta t, so that the ith time of your discrete representation is just I times, now I is a natural number, I times the time step. And so the solution is represented not on continuous time, but on these discrete sample times, which I also denote by just putting an index to the variable itself. And it is computed by iterating through time. And here's an example. So I would compute a new value xi plus 1 from the present value xi plus delta t times the function at that past value I or present value I. This is the simplest numerical algorithm that's called the forward Euler approach, because Leonhard Euler actually invented this approach. Actually, I'm not sure he did, but the name is attributed to him. And this is not an approach that you would usually use because it's not very efficient. We do that for reasons I will talk about later. We actually use it in some of our simulators because it's connected to sensory inputs and has to do with noise and reasons like that, that we still use this inefficient method. Inefficient in the sense that to get good precision, you have to have very small time steps. Well, if you do better approaches that are taking multiple different samples into account, not just the present one, then you can get away with larger delta t. And this formula, I'm not sure how intuitive it is, but you can sort of derive it intuitively very easily if you just recognize that the rate of change in discrete terms is called the differential quotient. You might know that from high school, right? That the approximation of this rate of change is just the delta x. So how much did x change in a time step? That's dx replaced by a finite delta x. And then the dt is the time step, delta t. So that will be an approximation in discrete time of the rate of change. And on the right-hand side, you're just inserting the order value of time because that's what you have. If you put in the newer value of time, you have an implicit equation, which is the backward Euler, which is actually a better procedure, but numerically more costly. But we just put in the past value here, and then you have here the past value, here the new minus the past value, and now you see just put the delta t on the other side, get this, and then you add the xi, you get that, and that's the Euler rule. So the new value is always just the old value. The increment to the old value is the dynamic, the function, times the time step. Okay, just as an advanced warning, if you do this with stochastic differential equations, the stochastic term is treated differently. It isn't treated like f, it goes with the square root of delta t. That's one reason why we use the Euler for stochastic differential equations, but I'm not introduced those formally here in this course. But it's actually not, it's often, people make mistakes about that very often when they deal with noise. So I wanted to show you a very simple piece of code, which I put on the web page. If you go to the web page, you already see that. It's a piece of MATLAB code, just again, to demystify, to show you how, what is in, so what's the core of doing these numerical simulations. So a very simple simulator in MATLAB. So it implements a simple equation, the one that's on the exercise sheet, and it's written, equation is written down here. Ignore all the green stuff, which is just common. So here, the right-hand side of the equation, I use very long variable names, is just equal minus alpha, just write that out, would be the Greek letter alpha, times x. Rather than type in x, I call that x variable. It's a very good idea in most programming languages to use long strings as names of variables, because then you can't make a simple typo and get a wrong formula. If you just call your variable t or u or so, then they have a real risk of that happening. And the problem with numerics is often in the end your program runs, but you don't know if it computes what you think it computes. So you've got to be sure that you typed in the right thing. That's why it's often a good idea to have variable names that are not just letters. So on the right hand side, you have minus x, here's a minus, see, minus alpha times x, and then I'm putting in the x at a particular time. I call the time step also not just I, because that could lead again to typos. I call it I time step, minus 1. This is the past value. That will be the right-hand side of the equation. And the Euler formula is here. So it says the variable at the new time step. So here I took the time step and then take the past value. The slide had time step plus 1 and the present value. So it's just how I start. If I start at 0 or at 1, here I start at 2. So the new value is equal to the just past value. We have a minus 1 here, plus the time step times the right-hand side of the equation, right? I've actually added here a noise term, as I just hinted, with a normal distributed rand number, noise strength, and there is the square root of the time step. So this is for some other exercise. And there's another version here which we don't need, actually. Can get rid of that. Okay, so that's the core of that, and the core means we're iterating through time. So time step goes, in this case, from 1, because I'm not starting at 0, I start at 1, and then the first new time step is 2. And then I go to the largest number of time steps. That's my loop. I give the initial condition as the value of the variable at time step 1. So enter then with the next time step, right? So here on the right-hand side, you would have the next time step. Now it starts at 2. So here you would have as the lowest value 2 minus 1, which is 1, which gives you that first time step. I have to set the parameters. So alpha is a model parameter. Noise strength, again, is just special. And here I'm not computing the number of time steps, not typing it in raw form. I'm actually using some time interval. Here, for instance, it goes from 0 to 10. And I'm fixing the time step in units of time, 0.05. And then I'm computing how many steps I need. So at this resolution, I need the final time divided by the number of time steps. That gives me how many time steps I have to make to reach, with that small time step, the final time. And here I'm just setting up time as an array that stores all the time steps. So 1 to n time steps, that gives me 1, 2, 3 until n time steps. So just so I can make nice plots where time shows up. And then the variable is a vector of the same length that is initially just all zeros. This clears just to delete any variable I had before. So I'm computing that, and then I'm plotting this very simply by making a figure, and the plot is on the x-axis I have the time steps, and on the y-axis I have the variable, and that creates the solution as a function of time. Now that's sort of the simplest thing that you have when you have to solve a differential equation. Of course, you would never really do that, right? There are actually in MATLAB, this is MATLAB, there are solvers that are much better. You can look at that. Let's say you can look at help. I think it's called OD solvers or something like that. Or no, it's help OD, I think. No, I'd have to search for what the keyword for that is, but there are a lot of solvers, or it's just solvers perhaps. Yeah, there's a whole page on that. So let's just run that. And I hope you get that figure. Do you get that figure as well? Does it come into the foreground?
Yes.
Yeah, great. Thank you. So this is the solution. It just plots, you know, I have from 0 to 10. I have, what do I count? 10 is the time. And in there should be, I think, n time steps is 200. There should be 200, time steps in here. And what you get is an exponential decay from my initial value 1 to 0. This is the equation that's on the exercise sheet that I already put online. So this is the numerical simulation. You could even produce some of the answers from that exercise sheet by taking this code and adapting to your needs to simulate it that way. For instance, I'm asking there you to vary alpha. And so for instance, I can make alpha smaller. So the slope of that dynamics is small. Then if I do that, then it will fall off much more slowly. And I can make it faster, for instance, by making it, for instance, maybe like this. Then it will fall off much more steeply. And I want to show you the extreme case of that. If I make this too fast, for instance, I don't know where it happens, somewhere here. And now, I know, sorry, this falls off very fast. Yes, that's fine. No, actually what I wanted to show you is go back to the original value. If I make the time step, vary the time step. So what really should happen is that the discretization doesn't matter. So as you vary the discretization time step, the solution should look the same. So let's run this again. This gives us this curve. And if I, let's say, take an even smaller time step, I should get the same curve. And then I know that I'm okay. Where's the other one? The figure 5 was the other one, I guess. Was it 4? No, wasn't this one. Did I delete the previous figure? Where is it? Yeah. Yeah. So these two are the two curves, same function, just a different resolution. You see with the naked eye there, very much similar, right? So this is the larger times. You always want to make time steps as large as possible. So this time step was just fine. But let's be more brutal. Let's take an even 10 times larger time step. And you may see that this is, I think it's actually still okay. Let's have a look. What was the previous figure? This one here was the very good resolution. It is the initial error here is just because the first time step we're looking at is already, you know, it has the first value is here. It just starts here. So this is not a significant error. But you see a little bit, you see little edges here. It's already a little less smooth, perhaps. And now let's be even more brutal and do like 1. And then you will see this is clearly no longer such a good approximation. You see this rough stuff here, right? And we can even be more brutal. Now it should really break down. Yeah, now it doesn't actually do anything anymore. It just computes one value, right? So that would be, of course, insane to have a time step that is so large, because as you will compute on the exercise sheet, this implies that the typical time scale of the system is 1 over that, which would be 2. So now I'm making faster steps than the typical time. So the 2 is probably the, you know, at 2 you still get some kind of decrease, but this is clearly no longer a good approximation of that exponential decay. Okay, so the code is on the webpage. If you have MATLAB, or you can have MATLAB for free, if, as I mentioned, you can play with that, and anyone who knows a little bit Python can very easily write a code like that, or much better than I do, and so on. Or you use just the solvers that are included in these various programs. Okay, that's all I want to do about numerics.